Hello, in part 2 of lecture 17, we are going to learn about low-pass filters in general. So the low-pass filters basically is a type of the filter which passes signals at frequencies lower than the cutoff frequencies. So I believe that I've explained to you what is meant by the cutoff frequencies. Okay, so looking at this magnitude plot of low-pass filters. So what we have here is the ideal magnitude plot. Yeah, what is meant by ideal? Ideal is a case whereby the separation between a pass band and stop band is very sharp, as shown here. Yeah, it's very sharp separation between a pass band and stop band, which is quite difficult to realize in a real case. Yeah, in a real case. Okay, so just to by using this ideal plot, we can then understand that low-pass filters is a type of a filter which only allow a signal at the lower frequency part, in this case lower than the cutoff frequencies, and it will then stop, or it will then prohibit a signal with higher frequencies to pass through the filter. Okay, so this is what we call as a low-pass filter. So the separation between the two band is what we call as a cutoff frequencies. Yeah. Okay, so there are two types of the low-pass filters, which are the series of RL circuit and the series of RC circuit. Okay, one important thing to be understood from this circuit is that for a series of RL circuit, we only have a single reactive component. Okay, so reactive component is whether it is L, inductor, or C, capacitor. So series RL circuit, we only have a single reactive component, a single inductor component, whereas for a series RC circuit, we have a single capacitor component. Okay, so basically, the number of reactive components will determine the number of the filter order. So in this particular case, since we have RL circuit and RC circuit, where both are having only a single reactive component, so that is why we consider this as a first order filter. Yeah, so basically the first order type and the number of reactive components do have relationship, which means that if we have two reactive components, for example, if we have RLC circuit, two reactive components, so this is equals to the second order of the filter. Yeah. So by now, I hope that you understand relationship between the number of reactive components and the filter order numbers. Yeah. Okay. So let's have a look at the first type of the filters, which is series RL circuit. Okay, so series RL circuit is where the output of this the output voltage is measured across the resistor. Okay, so when we have this case where the output voltage is measured across the resistor, so the transfer function will be equals to R over L over S plus R over L. So I left these terms, I left these to be mean the proving of this transfer function. I left this for you to solve it. Yeah, hopefully by now you have understood or you have understand how to obtain the transfer function for the given circuit. Okay, so one of the important things to be understand from this transfer function is that the transfer function for the low pass filter in this case consists only two components. The first one is a constant, and second component is a real pole. Okay, so we only have two components for the series of low pass filter, where we have a constant and we have a real pole component, for the circuit. Okay, so I don't want to proceed with this calculation of magnitude and phase. You can learn this on your own. Okay, so Yeah. Okay. The things that I want you to see from this equation here is that the cutoff frequencies, the cutoff frequencies can be calculated from a ratio of resistor R and L. Here, R over L will be the cutoff frequencies, and it shows that we can design the filters. We can design the filters by simply selecting values for the resistor R and the inductor L. Okay, so because we have proved that the cutoff frequencies value will be a ratio of R and L. So we can design the filters, we can design the filters according to our required cutoff frequencies by just change the R and the L values, Okay, so let's have a look at the block diagram for these filters. Okay, so this will be the common block diagram, magnetic plot diagram. Magnetic plot for the low pass filters. Okay, where we have a pass band. So this is a pass band where we have a constant amplitude. That should be your pass band. And this loop represent the stop band. So this is your pass band and this is your stop band here. Okay, so this is a common block diagram for a low pass filter. Okay, and the cutoff frequencies can be obtained by simply projecting the frequencies value, or by simply projecting the amplitude which is 3 dB lower than the passband amplitude. Then we can have the frequencies. For instance, if your amplitude plot is 0 dB, okay, so 3 dB lower will be the location of your cutoff frequencies. So by projecting a 3 dB or negative 3 dB value of the amplitude, we can then obtain the cutoff frequencies. Okay, so this is the common phase plot for a low pass filter. Okay, I don't want to proceed with this because by now you have understand how to plot the block diagram if you are given the transfer function equation. Okay, we proceed with the second type of the low pass filter, which is the RC circuit. So if you can recall from the previous block diagram of the previous type of the low pass filter, where we have the RL circuit, the low pass filter is obtained when the output voltage is measured across the resistor. Okay, but for the RC circuit, the output voltage is measured across the capacitor. Okay, so from this placement of the output voltage, the transfer function for these filters can be calculated to be look like this. Okay, so similarly, the low pass filter is having only two components. The first component is a constant, and second component is your real pole. So basically, for a low pass filter transfer function, there should be only two components. So this is for the first order type. So what we are discussing now is only for the first order type. Okay, so for the first order type of the low pass filter, there should be only two components. The first one should be a constant. The second one should be a real pole component. Okay, so similar to what we have learned before, for an RC circuit of low pass filter, the cutoff frequencies is calculated based on the equation of 1 over RC. 1 over RC. So based on this equation of the cutoff frequencies, again, we can design the filters according to our required according to our required cutoff frequencies. Okay, so we can design the filters according to our spec, our specification. I simply change the value of R and the capacitance value. Okay, so the symbol plot can be obtained for a series as in series of RL circuit, so we don't proceed with that. So we're going to have the first example for a low pass filters. Yeah, so in this example, we are given the transfer function straight away, where we have the transfer function is 10 over s plus 10. So based on this, you need to obtain the filter type using the Bode plot. And secondly, we need to obtain the 3 dB cutoff frequencies. Yeah, let's have a look at the solution for this example. Okay, so we are given this transfer function 10 over s plus 10. So that's what we have learned in the lecture 16. We need to change this transfer function into the pattern that we have here. Okay, so from here we have two components. We have a constant of 1 and we have a real pole at 10. Okay, so we can straight away sketch the Bode diagram. So that will be the first plot will be a amplitude plot, which is 20 log 1. So 20 log 1 will be 0 dB, so just a straight line at 0 dB value. And for the second plot, which is a real pole, we're going to have a 0 dB amplitude up to 10. And after 10, we're going to have a slope of negative 20 dB per decade. Okay, so this is a common plot for a real pole value. Yeah? So you can refer back to lecture 16 for better understanding on how we can obtain this Bode diagram. Okay, so based on this, when we combine these two plots together, we can have the final plot should be 0 dB up to 10, and after 10, we're going to have a slope of negative 20 dB per decade. So that will be the final plot for the said transfer function. So from here, we have two different bands. So less than 10 will be a pass band, a constant amplitude of 0 dB that will give us a pass band. Whereas for a frequency higher than 10 radian per second will be a stop band. So this slope here represents a stop band region, yeah, a stop band region. That should be a pass band region. So this is a low pass filters, yeah. So this diagram or this method plot represent the low pass filters. So in this particular case, we just estimate that the cutoff frequencies will be simply a 10 radian per second, yeah, because evidently it shows that we cannot obtain a 3 dB cutoff frequencies because this is just a sketching, yeah. So when we use a sketching method or sketching technique, we cannot detect exactly what should be the frequencies, the cutoff frequencies, because we cannot get the 3 dB amplitude, yeah, the 3 dB amplitude for that. Okay, right. So I hope you understand about this amplitude plot for the Bode diagram. For the phase plot, I believe that you can try to sketch that phase plot on your own. Yeah, you can refer back to lecture 16 to that plotting. Yeah. Okay, so after this, in part 3 of lecture 17, we are going to proceed with the high pass filter. Okay, thank you. See you after this.